So here's a question that seems almost obvious, right? Is space exploration inherently bad for the environment?
It really does feel like a paradox, doesn't it? You see
Mhm.
these enormous rockets igniting just this incredible spectacle of raw chemical power.
Yeah, just sheer force.
And your gut reaction, I think, for most people is, wow, that can't possibly be good for the planet. I mean, you're burning tons and tons of propellant just to fight Earth's gravity.
It's a totally understandable assumption. The energy scales we're talking about for getting anything into orbit are just mind-boggling. But, when you actually dig into the sources, what's really fascinating is the twist.
Uh-huh.
It turns out that the sheer necessity of building a truly sustainable way to live and work across planets has kind of forced the space industry toward technologies that are almost by accident surprisingly green friendly.
Exactly. It's not some sort of greenwashing effort or corporate goodwill necessarily. It's baked into the physics and the logistics of making interplanetary travel work efficiently and repeatedly.
Yeah, philanthropy isn't the driver here.
Not primarily, no.
Yeah.
The old way, the 20th century model of these bespoke, one-off disposable missions, usually burning refined kerosene, well, that just doesn't scale. If you want high cadence launches, like an airline, you need total reusability.
Right.
Kerosene just couldn't deliver that.
Right.
So the solutions they've had to develop for space logistics, things like methalox fuel, nuclear power for deep space, and advanced AI, these are actually starting to redefine what sustainable energy and architecture could even mean back here on Earth.
And that takes us straight into the three big pillars, the core technologies that are basically rewriting the whole rule book for space travel. These aren't just small improvements. They're like fundamental shifts needed to make this multi-planetary idea actually work.
Yeah, absolutely. So we should start with methalox. That's liquid methane, CH4, and liquid oxygen, LOX.
Yeah.
This is the key replacement for refined kerosene, the RP1 we just mentioned.
And crucially, it burns clean.
Super clean. And that solves the biggest single bottleneck, getting out of Earth's gravity well over and over again, reliably, sustainably, without massive engine rebuilds every time.
Okay, so that gets us off Earth. But once we're actually in space, the game changes, right? The power needs are different for crossing millions of miles.
Completely different environment, different
Yeah.
requirements. And that brings us to pillar number 2, the necessary move towards nuclear power. For getting between planets quickly and efficiently, especially for long trips, it's just the clear winner from a physics standpoint.
But there's a big caveat there, isn't there? These aren't little reactors you can just land anywhere.
No, absolutely not.
Hmm.
This introduces a really critical architectural point. These massive interplanetary ships, potentially the size of cities, they have to be built in orbit. And they have to stay in orbit or in deep space.
They never come back down into an atmosphere.
Never. They're true starships,
Yeah.
ships of the void, optimized purely for vacuum. They rely on other vehicles to shuttle stuff up to them.
Got it. And the third piece, the one that kind of makes this whole enormous scale possible.
That has to be AI and robotics. Artificial intelligence is it's the brain in the hands of this whole operation. It's not just for flying the ships autonomously where signals take too long.
Right, the light speed delay.
Exactly.
Yeah.
But AI is also crucial for the complex assembly of these giant structures in orbit, for managing the traffic, for maintenance, and importantly, for setting up the self-sustaining resource bases we'll need on places like the Moon or Mars.
So yeah, we're planning a really deep dive today. We want to go way beyond the kind of headlines you might see in popular media. We're going to get into the nitty-gritty physics of the different propellants, the real environmental questions like this issue of black carbon, which is actually a bigger deal than CO2 for rockets.
Really is, yeah.
And then look at the whole economic structure that has to underpin this massive logistics network.
It's really a complete reimagining of the space supply chain, moving away from that fragile, expensive throwaway model of the past
Yeah.
towards something much more resilient, maybe even a circular economy eventually, that uses resources from both Earth and, say, Mars.
Okay, fantastic. There's a lot to unpack there, but hang on. Before we properly light the candle on this deep dive, we just want to take a quick moment first to welcome you, our listener, and honestly to say thank you. The response we've been getting has been incredible.
It really has. We hear from so many people using these dives to get up to speed on really complex topics quickly.
Yeah.
And that feedback is genuinely motivating. It pushes us to make sure we're really digging into every source properly.
Absolutely. And speaking of growth and feedback, our marketing team, our crack marketing team, they shared a fun little statistic with us. Which is also kind of a challenge, I guess. It turns out only about 2%, just 2%, of the people listening regularly are actually subscribed to the show.
Interesting.
Yeah. And while the overall listening numbers are fantastic, which is great, that 2% figure kind of leads us into this classic chicken and egg problem.
Okay. I think I see where this is going. Video.
Exactly. We get requests all the time, and we love getting them, keep them coming, for video versions of these deep dives, with visuals, diagrams, maybe some cool B-roll footage to help make these dense concepts a bit clearer.
And we genuinely want to do that. It makes total sense for this kind of content.
We really do. But, creating high-quality video, especially for complex topics, takes a lot of time and resources if you don't have a big production team. Which we don't.
Right.
So the smart way to do it now seems to be using some of these new AI tools that can automate a lot of the heavy lifting in video creation. We've actually been looking closely at one called Mosaic AI Video Editor. That's mosaic.so. It looks pretty amazing, honestly. It can take audio like this and basically generate relevant visuals around it.
Okay, so the chicken and egg is you need the tool to make the videos to get more subscribers, but you need more subscribers to maybe afford the tool.
Pretty much, yeah. So this is where you, our fantastic listener, come in. We've set a goal. We need to hit 1,000 subscribers across our platforms. It sounds like a small number, maybe, but it's the benchmark we need to unlock the budget to actually purchase and implement tools like Mosaic.
Makes sense.
So here's the direct appeal. If you're getting value from this show, if you enjoy these deep dives, could you please just take 10 seconds right now and hit that subscribe button wherever you're listening.
It genuinely makes a huge difference on the platform side.
It's the single biggest thing you can do to help us grow and improve the show. And maybe share this deep dive in your WhatsApp groups or, with a colleague who needs to understand the future of space tech. Help us get to that 1,000 subscriber mark so we can finally start building the video version using mosaic.so. Your click really does translate into more and hopefully better content.
Okay. Important logistical note handled. Now, shall we dive into the actual architecture, this emerging interplanetary economy?
Let's do it.
Right. So when we talk about the future of space, it's crucial to understand we're not just talking about doing Apollo again, but maybe slightly cheaper. That whole high-cost, launch once-in-a-blue-moon model,
Yeah.
that's not the goal anymore.
No, the ambition, and you see this across major space agencies and the big commercial players, is what some sources call a logical emerging architecture. It's a fundamental shift in thinking, moving from just exploring to actually building an interplanetary economy.
An economy that implies logistics, supply chains, regular transport.
Exactly. And if you start thinking about space travel as primarily a logistics challenge, like running a global shipping company, you immediately see why those bespoke, one-off rockets just don't cut it. You need scale, you need reliability, and critically, you need specialization.
Specialization, meaning different vehicles for different jobs.
Precisely. Because the environment on a planet's surface dealing with atmosphere and strong gravity is radically different from the environment of deep space, the cold, hard vacuum between worlds. Trying to build one vehicle that's optimized for both is incredibly inefficient. Okay, so that leads to this two-part transportation model that seems to be emerging. A clear division of labor.
That's the core idea. Each system is designed and optimized for its specific operational environment. So, part one is the Gravity Well shuttle. You can think of it as the workhorse.
The heavy lifter.
The ultimate heavy lifter. This is a brutally powerful chemical rocket system, but crucially, it's designed to be fully reusable and operate at an extremely high cadence. Its job is very specific, but incredibly demanding.
Just getting stuff from the ground to orbit.
Exactly. Hauling massive payloads, maybe 100 to 150 metric tons per trip, out of Earth's deep gravity well and into low or medium Earth orbit. That payload could be habitat modules for a space station, complex machinery, components for bigger ships.
And fuel, right. Lots and lots of fuel.
Massive quantities of propellant. That's probably its main cargo, acting as an orbital tanker. Think of it like the freight train of this future economy, constantly shuttling resources uphill.
And you mentioned high cadence. What does that actually mean in practice? We're not talking about launches months apart anymore.
Oh, nowhere near. If the goal is to build, say, a self-sustaining colony on Mars, you need to lift not just habitats and supplies, but potentially millions of autonomous robots for construction, mining, maintenance.
Millions, wow.
That's the scale some projections are looking at. To achieve that kind of mass lift, the launch frequency for these workhorse shuttles needs to approach something like an airline schedule. We could be talking several heavy lift launches per week, maybe even daily eventually.
Okay, that level of speed and reusability is clearly the absolute linchpin for the whole thing.
It is. And that brings us neatly to part two, the in-space hub, or maybe call it the Starship. These are the long-haul vessels.
The ones that actually go between planets.
Right. Designed purely for long-duration, high-velocity travel across the vast distances of the solar system. They're likely to be hyper-efficient, probably using nuclear power, as we discussed.
And these are the potentially city-sized ones.
That's the vision. Colossal structures, assembled in orbit from modules brought up by the Workhorse shuttles, maintained and operated largely by AI and robotics. Because sending humans out to tighten bolts on a reactor in deep space is problematic.
Yeah, understatement. So if the Workhorse is the local freight train, the Starship is the giant ocean liner, the Trans-Pacific cargo freighter.
Perfect analogy. And this separation, this specialization, leads to probably the single most critical architectural rule of this whole system.
Which is?
These giant interplanetary starships, they never, ever land. They don't even get close to a major planet's atmosphere, except maybe high orbit at their destination.
They are truly ships of the void.
Absolutely. Their sheer mass, their specialized propulsion systems, especially if they're nuclear and their structures optimized for the vacuum, maybe with huge radiators, none of that is compatible with plunging through an atmosphere or enduring the stresses of landing in high gravity.
So they completely depend on the Workhorse shuttles meeting them in orbit.
Entirely. The shuttles act as ferries, bringing up fuel, cargo, maybe crew, transferring it over in orbit, and then heading back down. The Starship stays out in space, making the long journeys.
That makes so much sense from an engineering perspective. You don't compromise the design trying to make it do everything.
It's really non-negotiable if you want this to be economically viable and physically safe. You simply can't build a single ship that's optimized for both pushing thousands of tons across millions of miles of vacuum and handling the intense heat and forces of atmospheric reentry and landing. It would be monstrously complex and expensive.
So the whole infrastructure investment gets split then. You need massive ground facilities for launching and refurbishing the reusable workhorses really quickly.
And you need huge orbital facilities, assembly docks, fuel depots, maybe maintenance hubs for building and servicing the starships out there in space.
And both parts have to work together reliably, continuously, like clockwork, for this whole interplanetary economy idea to even get off the ground, literally.
That's the plan. It's ambitious, but it's logically coherent.
Okay, so let's zoom in on that first absolutely critical step, just getting off Earth. Escaping the gravity well, you said it's the foundational bottleneck.
It really is. It's the moment of peak energy demand in the entire journey profile. Until we solve that Earth-to-orbit, or ETO, problem of transportation, that is cheap, reliable, and truly high-cadence reusable, the whole dream of an interplanetary economy just stays a dream. It stalls right there on the launch pad.
And for decades, the standard solution for that first big push was refined kerosene, RP1, mixed with liquid oxygen. Kerolox. Why was that the go-to for so long? It wasn't just random, right?
No, not at all. There were very solid physics-based reasons why RP1 dominated first stages, especially for that initial climb to the thickest part of the atmosphere.
Okay, so what were the main advantages? You mentioned maximum thrust needed, but what specifically about RP1 made it suitable?
Well, it comes down to a couple of key things. When you're fighting gravity and thick air right off the pad, you need the maximum possible thrust squeezed into the smallest, most aerodynamic package possible. RP1 isn't actually the most efficient fuel in terms of specific impulse. That's kind of like the miles per gallon for rockets.
Right, how much push you get for each pound of fuel burned over time.
Exactly. RP1's specific impulse is decent, maybe in the 300 to 330 second range, but not spectacular. However, it has a fantastic density impulse.
Density impulse. Okay, but what does that mean? It packs a punch in a small volume.
Precisely that. RP1 is really quite dense for a fuel, around 0.81 grams per milliliter, much denser than other options like methane or especially hydrogen.
And why is density so important for that first stage?
Because it means your fuel tanks can be significantly smaller and lighter to hold the same mass of fuel compared to a less dense propellant. Think about rockets like the Saturn V or Soyuz or the Falcon 9 first stage. They all relied on Kerolox. Now, imagine if their fuel tanks had to be, say, 3 or 4 times larger just to carry the same amount of fuel energy, because the fuel itself was less dense. That extra tank size means extra tank weight, extra structural support, more aerodynamic drag.
And that eats into your payload capacity. The whole vehicle gets heavier just to carry the fuel container.
Exactly. So RP-1's high density allowed for smaller, lighter, more aerodynamically stable rocket designs, which is crucial for minimizing the mass you have to lift against gravity and push through the atmosphere.
Okay, that makes sense. Any other advantages?
Yeah, operationally, RP-1 was relatively simple. It's liquid at normal temperatures. It's not cryogenic. That simplifies the handling, the storage, the plumbing on the rocket, and the ground support equipment. It reduced complexity and cost compared to dealing with super cold cryogenic fuels. It was the proven, understood workhorse for decades.
Okay, so dense, powerful enough, easy to handle, sounds pretty good. So why the big push away from it now? What's the fatal flaw?
The flaw becomes absolutely critical the moment you demand true, rapid reusability. Like landing a booster, doing some quick checks, refueling it, and launching it again potentially within hours or days. RP-1 makes that virtually impossible because of one major problem: coking.
Coking, like soot.
Exactly like soot, but happening inside the most critical high-performance parts of the engine. Kerosene isn't a simple molecule. It's a complex mix of long hydrocarbon chains.
Right.
When you subject that mix to the incredible heat and pressure inside a modern rocket engine, especially in things like the preburner or the tiny cooling channels that line the nozzle and combustion chamber,
Yeah.
the kerosene literally starts to break down chemically. It undergoes thermal decomposition or cracking.
And this isn't just about having a bit of black smoke coming at the end. This is a chemical change happening within the engine hardware.
Entirely internal, and that's the problem. It doesn't just burn in completely like a smoky diesel engine. The intense heat actually causes these hydrocarbon chains to pyrolyze, forming hard, sticky, baked-on carbon deposits. That's the coke or soot, right onto the internal metal surfaces.
Okay, I can see how that wouldn't be good. Where does it build up the most?
It's particularly bad in the tiny high-stress pathways, like the fuel injectors, and especially within the complex turbo machinery, the turbo pumps that force the fuel and oxidizer into the combustion chamber at insane pressures.
And why is that internal soot buildup so catastrophic for quick reuse?
Well, first, coking rapidly degrades the engine's performance. These deposits mess up the flow patterns, they clog injectors, they reduce the efficiency of heat transfer in the cooling channels, which can lead to dangerous hotspots and even structural failure over time.
Okay, bad for performance and longevity.
But the killer for reusability is that after every single flight with a Kerolox engine, especially when pushed hard, you have to basically tear the engine down. You have to meticulously clean out all that baked-on carbon residue, inspect everything for damage caused by it.
Wow, after every flight.
Essentially, yes, if you want a high reliability. It's an incredibly slow, labor-intensive, and expensive refurbishment process. You can't just land, refuel, and fly again like an airplane.
Mm-hmm.
Kerosene imposes this unavoidable built-in delay and cost for cleaning and overhaul. It fundamentally prevents the kind of high-cadence, airline-like operations needed for that interplanetary economy.
Okay, so RP-1 is out if you want to fly frequently and cheaply. Enter the solution, Methalox. That's liquid methane, CH4, and liquid oxygen, LOX. Why is this the magic bullet for reusability?
It comes down to the sheer chemical simplicity of methane, CH4. It's the smallest possible hydrocarbon molecule, just one carbon atom and 4 hydrogen atoms.
Much simpler than the long chains in kerosene.
Way simpler. And because of that simplicity, when methane burns with oxygen, especially under the right conditions in a well-designed engine, the combustion is almost perfectly clean. It leaves virtually zero carbon soot, zero coking residue behind.
Ah, so no internal gunk building up.
Exactly. That clean burning property is the absolute game changer. It's the single most important factor enabling rapid turnaround. If you eliminate the coking problem, suddenly the idea of inspecting, refueling, and flying an engine again very quickly, maybe hundreds of times before needing a major overhaul, becomes physically possible.
Okay, clean burn is huge. But what about performance? Does it match up to RP-1?
It's actually better in terms of efficiency. Methalox offers a higher specific impulse than RP-1. You're typically looking at a range of maybe 340 to 370 seconds, depending on the engine design. So it's more efficient and it burns clean. It's a win-win there.
What about the density? You said RP-1's density was a big advantage. Methane isn't as dense, is it?
No, it's not. Liquid methane is significantly less dense than RP-1, around 0.42 grams per milliliter compared to RP-1's 0.81. So yes, you do need larger fuel tanks for the same mass of methane. That's a drawback.
So the tanks are bigger and heavier. Doesn't that negate some of the benefits?
It's a trade-off, definitely. The tanks need to be larger, which adds some mass and volume. However, Methane is still vastly denser and much easier to handle than the ultimate low-density fuel, liquid hydrogen, LH2.
Right.
So Methalox hits this kind of sweet spot. Its density is manageable. The tanks are bigger than RP1 tanks, but not outrageously so, especially with modern materials and design techniques. And you gain so much on the reusability and efficiency front that the density penalty is considered well worth paying. It's seen as the optimal compromise.
Okay, but methane is cryogenic, right? It has to be kept very cold to be liquid. RP1 wasn't. Aren't we just trading the complexity of cleaning engines for the complexity of handling cryogenic fuels? Why is that a good trade?
That's a really critical question, and it gets to the heart of operational philosophy. Yes, Methalox is cryogenic. Liquid methane boils at about nautical 162 degrees Celsius. So you absolutely need specialized insulated tanks, pipes, handling procedures, the whole cryogenic infrastructure.
Which sounds expensive and complicated.
It is an upfront investment, no doubt. But here's the difference. Dealing with coking is fundamentally a repair and maintenance cost and delay that happens after every flight. It's unpredictable, requires highly skilled technicians, involves engine disassembly. It's a recurring operational bottleneck.
Whereas cryo handling.
Cryogenic handling, while it requires careful engineering and specialized equipment, is primarily an infrastructure challenge and a set of predictable operational procedures. Once you've built the cryogenic ground systems and perfected the loading processes, they can be largely automated and are quite reliable. You're trading a constant, variable, labor-intensive repair cycle for a predictable, manageable, upfront infrastructure cost and standardized procedures.
Ah, okay. So the upfront investment in cryotech buys you long-term predictability and, crucially, that high operational tempo.
Exactly. The operating cost per launch drops dramatically once the infrastructure is in place, compared to the never-ending refurbishment cycle forced by kerosene coking.
Yeah.
It unlocks the economics of frequent flight.
And speaking of economics, what about the cost of the fuel itself? We're talking about huge quantities here. You mentioned maybe 4,800 tons of propellant for a single Starship launch example. Does methane cost less than RP1?
Significantly less, generally. Highly refined RP1 is a specialized petroleum product, almost like a boutique fuel. It's not cheap to produce in large quantities to the required purity standards.
Okay.
Liquefied natural gas, or LNG, which is typically about 95% or more pure methane, is a global energy commodity. It's much cheaper and more widely available than RP1. When you're burning thousands of tons per launch and aiming for multiple launches per week, that difference in bulk fuel cost becomes a massive economic factor.
Right, the fuel bill alone would be huge.
Huge. So the combination of eliminating the refurbishment nightmare, getting higher performance, and having access to a cheaper bulk fuel source, it really makes the Methalox choice almost an economic mandate for any business plan that relies on high-cadence heavy line.
Makes sense. We should probably just briefly touch on liquid hydrogen, LH2, just to sort of complete the picture. If it's the most efficient chemical fuel, why isn't that the choice for the first stage?
Right. LH2 definitely wins on pure efficiency. Its specific impulse can be incredibly high, potentially up into the 450s or even 465 seconds range in a vacuum-optimized engine. Its exhaust is just water vapor, H2O, which has a very low molecular mass, and that's key to high exhaust velocity and efficiency.
Sounds great.
It's fantastic for upper stages, operating purely in vacuum where maximum efficiency is everything and thrust levels can be lower. You see it used on the upper stages of rockets like Delta IV or SLS.
But not for the first stage, the workhorse climbing out of the atmosphere.
Almost never. The problem is its density. LH2 is extremely low density, only about 0.07 grams per milliliter. That's more than 10 times less dense than RP1.
Whoa. So the tanks would have to be enormous.
Absolutely colossal. And because hydrogen is so cold, liquid below -253 Celsius, and the molecules are so small, the tanks need complex insulation, vacuum jackets, and they still suffer from boil-off issues. Plus, hydrogen can make certain metals brittle over time, hydrogen embrittlement.
So huge, heavy, complex tanks, difficult handling.
Exactly. The sheer size and structural mass penalty of the required LH2 tanks, plus the handling complexity, just makes it impractical and volumetrically prohibitive for a reusable, high-thrust first stage that needs to be robust and turned around quickly.
So Methalox really does seem to hit that practical, cost-effective sweet spot for the specific job of escaping Earth's gravity well repeatedly.
That's the consensus driving the current generation of heavy-lift reusable rockets, yes. It's the enabling technology for the first part of that interplanetary architecture.
Okay, so our Methalox workhorse has done its job. It's muscled maybe 150 tons of cargo, or more likely a huge load of propellant, up into an orbital depot. Great. But now we face the second half of the problem. Getting that cargo, or maybe crew, across the millions, even hundreds of millions of miles between planets. Why are chemical rockets, even efficient Methalox ones, just not practical for that deep space leg?
It really boils down to two things: efficiency over long durations and transit time, especially for crew. Chemical rockets are fantastic for giving you a huge push quickly, getting off the ground, making a short burn to change orbits. They excel at high thrust.
Right, brute force?
Brute force, exactly. But they burn through propellant incredibly fast. When you're talking about a journey that takes months, like going to Mars, trying to use chemical rockets for the main propulsion segment means you have to carry an absolutely astronomical amount of propellant. The sheer mass of the fuel required makes the whole mission architecture incredibly inefficient, maybe even impossible for large payloads or reasonable trip times.
The fuel needed to carry the fuel becomes the problem.
Precisely. The tyranny of the rocket equation bites really hard on long trips. And for crewed missions, the longer you spend in deep space, the more you're exposed to dangerous radiation, solar particle events, galactic cosmic rays. Speed becomes a matter of health and survival.
Okay, so chemicals out for the long haul. This is where nuclear propulsion becomes basically the only viable game in town.
For efficient, relatively fast interplanetary travel, yes. It offers performance leaps that chemical systems just can't touch. And we need to distinguish between the two main types of nuclear propulsion being seriously considered, because they serve different purposes, reflecting those two types of traffic we mentioned: the fast crew transport and the slower heavy cargo hauling.
Right, the express train versus the freight train. Let's start with the faster option, the one you'd want for getting people to Mars quickly. Nuclear thermal propulsion, or NTP.
NTP is all about speed and relatively high thrust, at least compared to other advanced concepts. The core idea is surprisingly straightforward. You have a compact fission reactor, but instead of using its heat to generate electricity, you use the intense heat directly.
To do what?
To heat up a propellant gas, almost always liquid hydrogen, because of its low molecular mass, to extremely high temperatures, maybe 2,500 degrees Celsius or even more. This superheated, high-pressure hydrogen gas is then expelled out through a rocket nozzle, just like in a chemical rocket.
Ah, okay, so the nuclear reactor replaces the chemical combustion chamber as the heat source, but you're still expelling hot gas for thrust.
Exactly. But because the reactor can generate far higher temperatures than chemical combustion, and because hydrogen is so light, the exhaust velocity of that expelled hydrogen is much, much higher than you can get from chemical reactions.
And higher exhaust velocity means higher efficiency, higher specific impulse.
Massively higher. NTP systems can essentially double the specific impulse of the very best chemical rockets. We're talking potential live values in the 800s, 900s, maybe even touching 1,000 seconds, compared to maybe 450, 465 for the best chemical hydrogen-oxygen engines.
Doubling the efficiency, that's huge. What does that actually mean for, say, that crewed trip to Mars? How much faster is it?
It means you need far less propellant mass to achieve the necessary change in velocity delta for the trip. And that translates directly into significantly shorter travel times. A typical Mars mission using conventional chemical rockets might involve transit times of up to 9 months each way, depending on planetary alignments.
Which is a long time to be cooped up and soaking in radiation.
A very long time. NTP could potentially cut that transit time down to maybe 4 or 5 months. That reduction is absolutely critical for crew health. It dramatically lowers the total cumulative dose of deep space radiation the astronauts receive, making the mission much more survivable and reducing long-term health risks. For human exploration beyond the moon, NTP is widely seen as an enabling technology.
Okay, so NTP is the fast passenger service. What about hauling all the heavy stuff? The robots, the habitats, the construction materials? That sounds like a job for the slower, steady option, nuclear electric propulsion, or NEP.
That's right. NEP operates on a completely different principle. Here, you do use the fission reactor to generate electricity, but vast amounts of it, maybe megawatts or even tens of megawatts of continuous power.
Okay, so you have a powerful nuclear generator in space. What does it power?
That electricity is then fed to highly efficient electric thrusters. These aren't like chemical rockets at all. Things like Hall-effect thrusters or ion engines use electric and magnetic fields to accelerate tiny amounts of propellant, often heavy inert gases like xenon or argon, to incredibly high speeds.
These are the ion drives you hear about in science fiction sometimes, the ones that glow blue.
Pretty much, yes. They produce very low thrust. You wouldn't even feel it if you were standing next to one. It might be comparable to the force of holding a piece of paper in your hand.
So not useful for getting off a planet.
Absolutely useless for that. But they are incredibly fuel efficient. They are sippers, not gulpers. They achieve extremely high specific impulses, thousands or even tens of thousands of seconds, because they accelerate the propellant ions to such high velocities.
So low thrust, but they can keep thrusting for a very, very long time because they use so little fuel.
Exactly. They push gently, but they can push relentlessly for months or even years. This makes them ideal for moving enormous multi-thousand-ton cargo freighters across the solar system. They don't need to arrive quickly, they just need to move massive amounts of cargo efficiently. They spiral out slowly, build up speed over time, and then spiral in slowly at the destination. Perfect for robotic cargo.
And the need for these powerful reactors and often large radiator panels to get rid of waste heat that reinforces why these NEP ships have to be built in space and stay there.
Absolutely. These are not vehicles designed for atmospheres. Their power levels, their thermal management systems, a low-thrust nature, it all points to them being purely deep space vessels, assembled and operated far from Earth. Again, that segregation of roles is key.
Okay, so we have the Methalox workhorses hauling fuel up from Earth and these powerful nuclear NTP and NEP ships waiting in orbit or deep space. How do they connect? How does the fuel get from the shuttle to the Starship? That sounds like the role of the propellant depot solution.
That's the crucial logistical link. The fleet of reusable Methalox workhorse shuttles essentially acts as a continuous orbital tanker service. They make frequent, relatively low-cost flights carrying primarily propellant methane and oxygen up to large storage tanks or depots stationed in orbit.
Where would these depots be? Low Earth orbit? Higher up?
Probably in various orbits, depending on the architecture. Maybe some in LEO for initial aggregation, but likely larger ones in higher orbits, perhaps even out near the Moon, to serve as major staging points, well away from the busiest orbital lanes in Earth's radiation belts.
And these depots just stockpile the fuel.
Yes, they act as giant orbiting fuel dumps for gas stations. They aggregate the massive quantities of propellant needed for the interplanetary nuclear fleet. Remember, an NTP ship going to Mars still needs a lot of liquid hydrogen, even if it's more efficient. An NEP ship needs its xenon or argon. The depots collect all this from the frequent workhorse deliveries.
So the workhorse is like the local delivery truck network constantly restocking the regional warehouse, the depot.
Exactly. And then the big long-haul nuclear freighter, the Starship, comes to the depot, fills up its tanks with the aggregated supply, and then departs on its multi-month or multi-year journey.
Got it. The whole system relies on that constant, efficient flow. Cheap launches from Earth feeding the depots, which then fuel the high-performance interplanetary ships.
Precisely. The efficiency and critically the cadence of that Methalox first stage feeding the system is what makes the whole architecture economically feasible. Without cheap, frequent access to orbit, the depots remain empty and the nuclear ships stay parked. Hashtag Verfegai, AI, robotics, and the self-sustaining supply chain. Okay, so we've got the powerful reusable shuttles figured out with Methalox, and we have the efficient nuclear engines for the long haul across space. We have the fuel depots connecting them. But the sheer scale of building and operating an interplanetary economy, actually colonizing Mars or the Moon, none of that happens without the third crucial piece, the AI and robotics revolution.
Right. You mentioned AI is both creating the demand and providing the solution. Let's unpack that. How is AI creating the demand?
Well, think about actually building and running a base on Mars, or a large orbital station. Sending humans to do all the construction, maintenance, mining, and day-to-day operations is incredibly expensive, complex, and dangerous due to radiation and life support needs. Human oversight is slow, especially with communication delays.
So robots do the work instead.
Largely, yes. The only way to make these off-world outposts functional, safe, and economically viable is to rely heavily on an autonomous robotic workforce. We're talking about robots that can build habitats using local materials, deploy solar arrays, maintain power grids, operate mining equipment, maybe even perform scientific experiments, all with minimal, direct human supervision.
And lifting all those robots is the demand.
Exactly. The need to transport millions of these sophisticated, construction-capable, AI-driven robots from Earth to orbit and then onwards to the Moon or Mars. That is what creates the massive, sustained demand for those high-cadence Methalox workhorse launches we talked about. The interplanetary economy, at least initially, is largely built on delivering the robotic workforce.
Okay, so AI drives the need for massive lift capacity. How does it then provide the solution for managing this incredibly complex logistics network?
In multiple ways. First, autonomous operation is non-negotiable for the deep space vessels. Imagine an NTP ship arriving at Mars. The round-trip light delay for communications could be anywhere from 8 to 40 minutes.
Yeah, you can't joystick that landing in real time from Houston.
Not a chance. So AI pilots and sophisticated autonomous mission control systems have to handle navigation, critical orbital insertion burns, hazard avoidance, maybe even docking maneuvers, all by themselves, making real-time decisions based on sensor data.
And what about closer to Earth, managing all those workhorse launches?
AI is essential there too. For managing the increasingly crowded orbital environment, tracking satellites and debris, deconflicting trajectories, for optimizing the launch and landing procedures of the reusable shuttles, and for diagnostics and maintenance. AI-powered systems can predict when a component on a rocket engine is likely to fail, allowing for proactive maintenance. AI-driven robotic systems in the ground facilities can perform much of the inspection and refurbishment work needed between flights, helping achieve that rapid turnaround.
And you also mentioned AI helping with the actual construction of the giant starships in orbit. That sounds incredibly complex.
It is. Assembling city-sized structures in zero gravity, welding massive modules together, connecting power and life support systems. That's not a job for humans in bulky spacesuits if you want efficiency and safety. It requires fleets of specialized AI-controlled construction droids working collaboratively in the vacuum. Maybe even droids that can self-replicate to some extent, using resources mined in space.
Wow. And does AI play a role even earlier in designing the hardware itself?
Absolutely. This is a huge area right now. AI-driven generative design. Engineers can essentially tell an AI the performance requirements, the material constraints, the loads a component needs to withstand. And the AI can explore thousands, even millions, of possible geometric designs, often coming up with incredibly lightweight, strong, and efficient structures that a human might never have conceived of.
Like optimizing the internal structure of a fuel tank for maximum strength with minimum weight.
Exactly. Or designing the intricate cooling channels inside a rocket nozzle, or optimizing the layout of components within a spacecraft. AI can iterate on designs incredibly quickly, leading to better, lighter, more efficient hardware developed much faster than traditional methods allow.
Okay, so AI is the brain, the pilot, the mechanic, the construction crew, and even the design engineer. Now, how does this all connect to making the whole system truly self-sustaining? That brings us to In-Situ Resource Utilization, or ISRU.
ISRU is the absolute key to breaking free from total dependence on Earth. It's the transition point from just having an expensive, far-flung outpost to establishing a genuinely self-sufficient, permanent presence off-world.
Using local resources on the Moon or Mars to live off the land, essentially.
Precisely. And again, those AI-driven robots are the vanguard. Their first major job on, say, Mars won't be science. Probably it'll be heavy engineering. They'll need to use the Martian soil, the regolith, to 3D print landing pads, construct habitats, maybe bury them for radiation shielding.
And crucially, deploy and operate the ISRU plants.
That's the cornerstone of self-sufficiency. Setting up chemical processing plants that can extract useful resources from the Martian environment. Particularly water ice, which we know exists in large quantities just beneath the surface in many areas, and carbon dioxide, which makes up about 95% of the thin Martian atmosphere.
And what do they make from that water ice and CO2?
They make rocket fuel. Specifically, they make more methalox, the same fuel our workhorse shuttle uses. This is where the choice of methalox becomes strategically brilliant.
How does it work? What's the process?
The core chemical process is called the Sabatier reaction. It's well-understood chemistry. The ISRU plant first needs energy, probably from solar panels or maybe a small nuclear reactor brought from Earth initially. It uses that energy to mine the water ice and melt it.
Okay, so you have liquid water.
Then you use electrolysis, running an electric current through the water to split the H2O into hydrogen gas, H2, and oxygen gas, O2. The oxygen is useful for breathing, but it's also the oxidizer component of methalox.
Got it. So you have oxygen and hydrogen. What about the methane?
That's where the Sabatier reaction comes in. You take the hydrogen gas, H2 you just produced, and you react it with carbon dioxide, CO2, pulled directly from the Martian atmosphere, usually over a catalyst like nickel, and at elevated temperature and pressure.
And what does that reaction produce? Can you give us the simple chemistry?
Sure. The basic reaction is CO2A2, carbon dioxide, plus 4H22, 4 molecules of hydrogen, yield CH4I3, 1 molecule of methane, the fuel, plus 2H2O2, 2 molecules of water.
Ah, so it makes methane and water.
Exactly. And that water is precious. It can be fed back into the electrolyzer to produce more hydrogen and oxygen. It's a beautifully elegant cycle. You're using Martian CO2 and Martian water ice plus energy to produce methane fuel and oxygen oxidizer.
So the CO2 that we're desperately trying to reduce here on Earth actually becomes a primary feedstock, a valuable resource on Mars.
It absolutely does, along with water ice. It's the foundation of the local manufacturing capability for propellant.
And this enables the ultimate logistical trick, self-refueling.
That's the payoff. Imagine our workhorse shuttle lands on Mars, having delivered its cargo of robots or supplies from Earth. Instead of just sitting there, useless, or needing a massive amount of propellant sent all the way from Earth for its return trip,
It drives over to the local ISRU plant.
and fills up its tanks with locally manufactured Mars-made methalox. It refuels itself using Martian resources for the journey back to Earth orbit.
Wow, that closes the loop. That establishes the first real interplanetary supply chain. It's not just a one-way delivery anymore.
Exactly. It transforms the economics entirely. It means the transport system itself becomes partially self-sustaining. And the fact that the Earth-to-orbit shuttle and the Mars surface refueling system can use the same propellant clean-burning ISRU-producible methalox is just a massive strategic advantage. It simplifies the entire architecture.
That common fuel standard is key. Okay, this paints a picture of a remarkably integrated and potentially sustainable system.
So remember where we started this whole deep dive, with that seeming paradox. Is space exploration fundamentally dirty, inherently bad for the environment?
Yeah, the image of the giant fiery rocket launch.
Right. But now, having gone through the actual emerging architecture, the shift to methalox, the necessity of nuclear for efficiency, the reliance on AI, the goal of ISRU, we can really challenge that old, maybe outdated notion that space exploration and environmentalism have to be enemies.
It seems like that conflict was mostly tied to the old way of doing things, particularly the reliance on kerosene fuel in the 20th century.
I think that's largely true. What we're seeing now is a fascinating convergence. The technologies that are absolutely required to make interplanetary civilization economically feasible and logistically possible. Things like extreme reusability, high efficiency, closed-loop systems, manufacturing fuel off-world. These are inherently driving the space industry towards greener solutions.
The economic imperative and the environmental benefit are starting to align, maybe out of necessity rather than pure altruism.
Precisely. And the most compelling environmental argument for something like methalox isn't just, oh, it enables reuse, which saves resources. It's that it directly addresses the primary climate impact associated with rocket launches themselves.
Okay, let's get specific here. What is the actual main environmental concern when a rocket launches? Most people probably assume it's the carbon dioxide, the CO2 emissions.
And CO2 is certainly a greenhouse gas, and rockets do produce it. But when you look at the scientific studies analyzing the atmospheric warming potential of rocket emissions, the finger points much more strongly at something else, especially from kerosene-burning rockets.
Which is?
Black carbon, basically soot. Tiny particles of unburnt carbon that are injected directly into the very high layers of the atmosphere, particularly the stratosphere.
Higher than airplanes fly.
Generally, yes. Rockets deposit these emissions much higher up than typical aviation. And the problem is, black carbon behaves very differently in the stratosphere than it does lower down, or even compared to CO2.
How so? Why is soot way up there so much worse?
It's all about how it interacts with sunlight, what scientists call radiative forcing. Black carbon particles are incredibly effective at absorbing incoming solar radiation. They literally soak up heat from the sun. When these particles are sitting high in the stratosphere, they trap that heat up there, directly warming that layer of the atmosphere.
Okay.
While these soot particles don't last forever in the atmosphere, their warming impact per particle during their lifetime is extremely high, much higher than the equivalent mass of CO2 over the same short period. Because RP1, kerosene, is this complex hydrocarbon mix that burns incompletely.
It produces a lot of this black carbon soot.
Exactly. It essentially dumps significant amounts of this potent, heat-absorbing black carbon directly into a very sensitive, high-altitude part of the atmosphere where it can do the most warming damage in the short term.
Okay, so that's the problem with kerosene. How does methane compare?
This is the key environmental advantage. As we discussed, methane, CH4, is a much simpler molecule. It burns far, far more cleanly, especially in modern, well-designed engines. It produces less CO2 per unit of thrust compared to kerosene, but the absolutely critical difference is that it produces virtually zero black carbon soot.
No soot means no injection of those highly warming particles into the stratosphere.
Precisely. By eliminating the primary warming mechanism associated with rocket launches, that stratospheric black carbon deposition methalox rockets fundamentally become a much greener propellant choice from a direct atmospheric climate impact perspective. It's not zero impact, there's still CO2 and water vapor, but it tackles the biggest known problem head on.
That's a very tangible science-based improvement, not just marketing speak.
It's a direct consequence of the cleaner combustion chemistry.
Okay, so Methalox is cleaner burning, which is great, but you also mentioned earlier that the Methalox architecture kind of future-proofs the energy supply chain. How does it do that? Can we actually detach space launch from fossil fuels entirely using methane?
Yes, and that's probably the ultimate long-term environmental advantage. Because methane is such a simple molecule, CH4, unlike complex kerosene, we can actually synthesize it. We can make methane without drilling for natural gas. This opens up clear pathways to carbon neutrality for the entire launch system.
Okay, how would that work? What's the main route to synthetic carbon-neutral methane?
The most promising pathway is often called synthetic methane or e-methane. The E stands for electrofuel, basically.
Okay.
The process aims for a truly circular fuel economy. You start by producing green hydrogen. That means using electrolysis to split water into hydrogen and oxygen, but powering that electrolysis only with renewable energy sources, solar, wind, geothermal, hydro. No fossil fuels involved in making the hydrogen.
Okay, so you have carbon-free hydrogen.
Then you take that green hydrogen, you combine it with carbon dioxide. But here's the trick. You use CO2 that has been captured either directly from the atmosphere using direct air capture technologies or captured from industrial point sources, like a cement plant or a power station.
Ah, so you're using CO2 that was either already in the atmosphere or was about to be emitted anyway.
Exactly. You then react that captured CO2 with your green hydrogen using, guess what?
Let me guess. The Sabatier reaction again?
The very same. Sabatier reaction takes the captured CO2 and the green H2 and synthesizes them into CH4 methane and water.
So when you launch a rocket using this e-methane, the CO2 that gets released back into the atmosphere is essentially the same CO2 that was captured to make the fuel in the first place.
Precisely. You create a closed carbon loop. It's effectively carbon-neutral propulsion. Now today, green hydrogen and direct air capture are still relatively expensive, so e-methane costs more than drilling for natural gas.
But the costs are coming down.
Rapidly. As renewable energy gets cheaper, electrolyzer technology improves, and carbon capture scales up, driven partly by climate policies, e-methane is projected to become a competitive, scalable, high-density liquid fuel. It allows the Methalox workhorse fleet to operate potentially with zero net carbon emissions. It's a future-proof fuel choice.
That's incredibly powerful. And wasn't there another, maybe more organic pathway you mentioned? Something about cows.
Ah, yes, the delightfully down-to-earth approach. Biomethane, sometimes called liquid biomethane or LBM, this really highlights the flexibility of methane.
So methane from biological sources.
Exactly. The sources we looked at mentioned a Japanese startup, for example, that has actually done successful rocket engine static fire tests using LBM derived entirely from biogas. And that biogas was captured from processing organic waste, specifically, in their case, manure from local dairy farms.
Wait, seriously, rocket fuel made from cow manure?
Literally, yes. You capture the methane naturally produced during the decomposition of organic waste, like manure, sewage sludge, or food waste. You purify it to get high-grade biomethane, liquefy it, and voila, you have LBM, which is chemically identical to LNG or e-methane.
That's amazing. Talk about closing the loop.
It's the ultimate in local circular economy thinking, isn't it? Taking a problematic waste stream and turning it into high-performance, clean-burning rocket fuel suitable for reusable engines. The supply chain could literally go from the farm to the biogas plant to the launch pad. It shows methane can be sourced sustainably in multiple ways.
Okay, so Methalox itself is cleaner, and its supply can be made carbon neutral through e-methane or even sourced from waste via biomethane. That tackles the launch impact. But what about the other side of the coin? How does space exploration actually help environmentalism here on Earth?
This is maybe the most direct and undeniable symbiosis. Our ability to even understand, monitor, and manage global environmental challenges is now fundamentally dependent on space-based technology.
You mean Earth observation satellites?
Exactly. Satellites orbiting Earth provide the objective, large-scale, often continuous data we absolutely need to track things like deforestation rates, glacial melt, sea level rise, atmospheric pollution, ocean temperatures. The list is endless.
Monitoring the planet's vital signs.
Precisely. Managing resources like freshwater distribution, tracking wildfires, monitoring air quality over cities, we rely on satellite data for all of that. And the AI systems we talked about are becoming crucial for processing the sheer volume of data coming down from these satellites, extracting meaningful patterns and actionable insights about our planet's health with incredible speed and accuracy.
So without space technology, our whole understanding of climate change and environmental pressures would be patchy, local, maybe anecdotal, instead of global and data-driven. Yeah.
Absolutely. We simply wouldn't have the comprehensive picture we have today without those eyes in the sky.
And there's also that more psychological, maybe philosophical impact too, right? The overview effect.
Yes, that's a really powerful point that comes up often. The profound cognitive shift that astronauts report experiencing when they see Earth from space, this fragile, beautiful blue marble hanging in the blackness
Yeah.
with no visible borders.
Just a single interconnected system.
Exactly. Seeing the thinness of the atmosphere, the obvious finitude of the planet. Many astronauts talk about how this perspective shift instilled in them a deep sense of responsibility for protecting Earth. And you can genuinely trace a line from some of the iconic images taken during the Apollo program.
Like Earthrise or the blue marble photo.
Those specific images, yes. They became galvanizing symbols for the modern environmental movement in the 1970s. They helped popularize the whole concept of Spaceship Earth. This idea that we're all crewmates on a single finite vessel traveling through space. Space exploration didn't just give us data, it gave us a powerful new perspective on our home.
So bringing it all together, it really seems the narrative is flipping. The very technologies we need to become a sustainable, multiplanetary species, things like highly efficient closed-loop life support systems for habitats, advanced AI for automation and resource management, clean and manufacturable fuels like e-methane or biomethane.
These are the exact same types of technologies that are critical for ensuring our long-term sustainability right here on Earth. The engineering challenges of keeping humans alive and thriving efficiently on Mars directly drive innovation in areas vital for tackling climate change and resource management back home.
The pursuit of space efficiency is driving terrestrial sustainability. It's a fascinating feedback loop.
It really is. That synergy between Methalox for clean ascent, nuclear for efficient transit, AI for intelligent operation, and ISRU for self-sufficiency. That whole package isn't just about getting to Mars. It's about developing the blueprint for a more sustainable technological future, wherever humans happen to live.
And it starts with that Methalox AI-powered workhorse, lifting humanity's robotic helpers, and eventually us, cleanly and efficiently out of the gravity well, setting the stage for that multiplanetary future while cleaning up the very first step of the journey. Hashtag outro.
So when we step back and look at this whole re-architected system, this blend of cleaner chemical rockets, efficient nuclear drives, pervasive AI, and living off the land with ISRU, what does it all really mean for us, for you listening?
Well, I think it means we're potentially charting a course towards a future that's defined less by the old fears of scarcity and environmental limits, and more by the kind of innovation that necessity breeds. Innovation that could lead to, well, a new kind of abundance.
Yeah, imagine that. A future of green abundance. Maybe, eventually, we can bring resources back to Earth from space that are rare here, certain metals. Perhaps helium-3 from the moon for future fusion reactors. Who knows? That could fuel incredible new waves of manufacturing and technology.
But maybe even more profound than bringing stuff back.
Is the idea of spreading the most precious and complex thing we know of life itself, our biosphere. Taking that first step to establish it on another world, ensuring its survival beyond a single planetary cradle. Then maybe expanding to other planets, other solar systems.
And who knows, maybe eventually reaching across intergalactic distances. It sounds like science fiction, but the foundational steps are being laid now.
The physics is aligning with the engineering possibilities. The economics are starting to make sense, driven by reusability and AI. The technology is maturing rapidly. We're genuinely seeing the shift from being a species confined and vulnerable on one small planet towards becoming a more resilient multi-planetary civilization.
The move to Methalox, embracing nuclear for deep space, leveraging AI everywhere that's forging the pathway.
Sky is not the limit anymore.
Not at all. It's becoming the highway.
Mm.
And speaking of pathways and journeys, just before we sign off, a quick return to our own mission control message here on the ground.
Right. If this conversation, this deep dive into the future space architecture resonated with you, if you found it valuable trying to piece together how all these technologies fit together,
Then please remember our goal to bring you even better content, including those video versions with visuals that so many of you have asked for.
and the key to unlocking that is helping the show grow just a little bit more. If you subscribe, if you share this episode with someone who'd find it interesting, you directly help us reach that target needed to get the tools to make it happen.
Yeah, specifically that Mosaic AI video editor tool we mentioned, Mosaic.so. We're genuinely excited about its potential. Imagine feeding it the audio link from this discussion, and it just automatically creates relevant, high-quality, AI-generated B-roll footage and helps streamline the whole complex video production process.
It would make creating those visual deep dives feasible for our small team, making the content easier to understand and more engaging.
We really do want to bring you those videos, but we honestly need your support to get the funds for the tools. So if you haven't already, please take those few seconds, hit subscribe, maybe leave a rating, share the show. It all helps enormously.
Okay, until our next deep dive then.
Maybe take a moment, look up at the sky, and imagine yourself on one of those future space voyages. Charting a course between worlds, powered perhaps by clean e-methane, guided by smart AI.
Houston